Hello children, welcome back. Your Vanashri ma'am is here with sound part 2. Now in part 1 I have discussed about echo and the determination of speed of sound by the method of echo, that is using formula V is equal to total distance travelled by time taken. Okay. Now we will learn about uses of echo. Uses of echoes. Now echo has many applications, sound ranging and echo depth sounding, and let us discuss one by one using ultrasonic waves. Now the ultrasonic waves that are frequency about 20 kilohertz are more energetic than the audible sound. So the properties of ultrasonic waves, you must know, they can travel undeviated through a long distance. Okay, then they can be confined to a narrow beam. They can be made to travel in a narrow beam. They are not easily absorbed in a medium. Now the audible sound waves of that is their frequencies from 20 hertz to 20 kilohertz do not possess these properties. However, the ultrasonic waves in a medium have the same speed as the speed of audible sound in the medium. So there is no difference in the medium, but the other properties, like they can travel undeviated through a long distance, they can be confined in a narrow beam, they are not easily absorbed in any medium. These properties are not possessed by normal audible sound waves. Okay. So now the first use is use of echo by bats. Use of echoes by bats, dolphins, and fishermen. Okay. Now animals have different audible ranges of frequency, like bats, dolphins, dogs have much higher audible range, okay, than the human beings. Bats can produce and detect sound of very high frequency, okay, so like up to about 100 kilohertz. Bats fly with speed much lower than the speed of sound. The sounds produced by the flying bats get reflected back from an obstacle in front of it. Okay, so the bats produce sound while flying. They flap their wings. Okay, so sound produced by the flying bats gets reflected back from an obstacle in front of it. Suppose they are inside a cave. So the cave wall is there, suppose, in front of them. If a bat is moving in the direction of the wall of the cave, then the sound that gets reflected by the cave wall. With that, the bat comes to know that there is a obstacle in front of it. So it will change its direction. By hearing the echo, bats come to know, even in the dark, the location of the obstacle. So they turn from their path and fly safely without colliding with it. This process of detecting obstacle is called sound ranging. Okay. So what is sound ranging? In sound ranging, the sound waves are sent. When they get reflected by an obstacle and come back from the echo of it, they come to know that there is an obstacle in it. I mean, in that direction. Now, dolphins detect their enemy and obstacle by emitting the ultrasonic waves. So, the dolphins themselves emit ultrasonic waves, and hearing their echo, they come to know that there is a presence of obstacle or enemy. They use ultrasonic waves for hunting their prey also. A trawlerman or fisherman sends ultrasonic pulse from a source, a very high frequency vibrator, which is kept in the boat, into the sea, and receives the pulse reflected from the shoal of fish in a detector. The total time t of the to and fro journey of the pulse is calculated by using the relation d is equal to Vt upon 2, where V is taken nearly as 1400 meter per second, that is speed of ultrasonic waves in seawater. So in this way they can locate the position of a fish, shoalfish, so that they can catch it easily. Okay. So the second use, this is the first use. Second use, use of echoes by sonar. Now, sonar, the full form of sonar is sound navigation and ranging. Sonar, full form, sound navigation and ranging. So, SONAR, that is the full form of sonar. There is a very important question, 1 mark question they ask. What? So this is a very important question, sonar. Okay. Now, what do they do? The ultrasonic waves are sent in seawater in all directions from the ship. These waves are received after reflection from an obstacle such as an enemy submarine, iceberg, sunken ship, etc. To find the distance of the obstacle from the ship, the time interval t between the instant when the waves are sent, okay, and the instant when the waves are received after reflection from the obstacle is measured. Now, the distance d of the obstacle from the source is then calculated using the formula d is equal to Vt upon 2, where V is the speed of the ultrasonic waves in water and the depth of the sea also can be found by this method. The process is then called echo depth sounding. Echo So echo depth sounding, what they do? Again, this in the ultrasonic waves. Those waves reach the bottom of the sea and reflect back and come back. And from the time calculated to, from the time sound waves, ultrasonic waves take to from the surface to the bottom and to back. From that we calculate the distance or the depth of the sea. Okay. So these are the uses of echo. Now we will be learning about an important concept called natural damped and forced vibrations, and also we will be learning about resonance. Okay, again important. Okay, now natural vibrations. The periodic vibrations of a body in the absence of any external force on it are called natural or free vibrations. So, they are natural vibrations in the absence of any other external force. If there are periodic vibrations of a body, if a body is vibrating without the influence of any external force, then those vibrations are called natural or free vibrations. So, what are they? The periodic vibrations of a body in the absence of any external force. That is important. In the absence of any external force on it means on the vibrating body, are called natural or free vibrations. Natural or free vibrations. Okay, so a body, suppose it is clamped at one point, when disturbed slightly from its rest position, starts vibrating. You all know that. The vibrations so produced are called natural or free vibrations of the body. So, the period or frequency of vibration depends upon the shape, size or structure of the body. The time period of the body is called its natural period and the frequency is called its natural frequency. A body capable of vibrating has a constant natural frequency of its vibration and its amplitude of vibration also remains constant. Okay. So, anyway, so basically natural vibrations are those vibrations of a body happening in the absence of any external force on it. Now, examples of natural or free vibrations: if the bob of a simple pendulum is displaced slightly from its mean position or rest position, it starts vibrating. Okay. Suppose this is the rest position O. Now, if you simply little displace it a bit, then suppose you pull it up to here, and leave it. So, it will start vibrating. It will come back, go, again come back and continue. Okay. So, these are natural vibrations. Okay. Then a load suspended from a spring, when stretched or compressed and then released, start vibrating with its natural frequency. Then when a tuning fork is struck against a hard rubber pad, it vibrates with its natural frequency. When air column in a flute or organ pipe is made to vibrate, it vibrates with its natural frequency, which is again example of natural vibrations. When the string in the instruments like sitar, violin, sonometer, etc. is once plugged, the transverse vibrations of the definite natural frequency are produced in the string. So these are all examples of natural vibrations. When we strike the keys of a piano, various strings are set in vibration, each at its own natural frequency. A string of a given length stretched between its ends under a given tension can be made to vibrate in different modes by plucking the string at different points. If you pluck it, it starts vibrating. Okay? Then, nature of natural vibrations. The natural vibrations, okay. Now let me discuss about the nature of natural vibrations. Now these natural vibrations have the same constant amplitude and frequency. So natural vibrations have constant amplitude and frequency. That means if an object, if any body is set in vibratory motion, it will continue vibrating with the same amplitude and with the same frequency. So that is why natural vibrations will always have same amplitude, same frequency throughout. Now if you plot a graph, displacement time graph for a natural or free vibration, it will look like this. Let me draw. Okay, so if you take time t on x-axis, amplitude or displacement on y-axis, then if you plot, then you will, if you plot the vibrations or natural vibrations of a body, then you will find the graph will be something like this. So the vibrations of a constant amplitude can occur only in vacuum. Since in practice it is very difficult to have vacuum, it is very difficult to realize such vibrations in practice. As a matter of fact, the surrounding medium offers resistance to the motion, so the energy of the vibrating body continuously decreases. That is why a simple pendulum, once set in motion, does not continue to vibrate because of the friction of the air around it and the atmosphere around it. Okay, so these are about natural vibrations. Now we will learn a new term called damped vibration. Damped vibration. The periodic vibrations of a body of decreasing amplitude in presence of a resistive force are called damped vibrations. So because of some resistive force, the vibrations keep vibrating with decreasing amplitude. So the amplitude of the vibration keeps decreasing with time because of the resistive force. Then those vibrations or such vibrations are called damped vibrations. Okay, so in damped vibrations, two forces act on the body, the restoring force and the frictional force. There are two forces acting on the body. Restoring force means it tries to come back to its original position, to restore to its original position. And the resistive force or frictional force are the forces opposing the vibrations. Okay, so that is our common experience. When a body is set to vibrate in a medium, the amplitude of vibrating body continuously decreases and ultimately the body stops vibrating. Such vibrations are called damped vibrations. So definition of damped vibration is the periodic vibrations of a body with decreasing amplitude. In presence of resistive force are called damped vibrations. Now, if you again plot a graph for these damped vibrations with displacement on the y-axis and time on the x-axis, it will look like this. So, displacement is taken on the y-axis. So this is plus a minus a and time is taken on the x-axis. Then here, like in natural vibrations, the amplitude was constant throughout. Here you will find that the vibrations keep on decreasing. Like this. So amplitude is decreasing. Okay, and ultimately the body comes to a stop. So this displacement time graph is of damped vibrations. Okay, this is the displacement time graph of damped vibrations. The earlier one was displacement time graph of natural vibrations. Now, examples of damped vibration. Just pull the branch of a slim branch of a tree, pull it down and release it. It makes damped vibrations. After some time, it will stop vibrating. A tuning fork, when stroked on the rubber pad, and if you release it, it will start vibrating for some time, but it will not continue forever. It will continue forever only in ideal situation when you can create a perfect vacuum. But where there is no resistive force, then it will continue to vibrate. But that is very theoretical or not possible, practically not possible. So because of the not because we cannot achieve perfect vacuum. So anyway, so these are even the simple pendulum bob, as I told you, after some time it will come to stop. So the vibrations of a spring, these are all examples of damped vibrations. Okay, so now we'll learn about the difference between natural vibration and damped vibration. Differences between natural and damped vibration. In natural vibration, as I told you, the amplitude of the natural vibration remains constant, whereas in damped vibration, the amplitude of the vibrations keep reducing or decreasing. Okay, so amplitude remains constant in natural vibrations, whereas in damped vibrations, amplitude keeps on decreasing in damped vibrations. That is the first point of difference. Then you have in natural vibration there is no loss of energy, but in damped vibration there is loss of energy in the form of heat. Now, so no loss of energy, and here there is loss of energy, where in damped vibrations. No loss of energy in natural vibration. Okay. Then in natural vibration, no external force acts on the vibrating body, whereas in damped vibration, in addition to restoring force, a frictional force or a damping force acts on the body. Now, in natural vibration, the frequency of vibration depends upon the size and shape of the body, whereas in damped vibration, the frequency of vibrations is always less than the natural frequency. Okay, so these are the differences between damped and natural vibrations. Now we will learn a new term called forced vibration. Forced vibrations. The vibrations of a body which take place under the influence of an external periodic force acting on it are called forced vibrations. Okay, so the vibrations of body which take place under the action of a periodic external force. See, in damped vibration also they are happening in the presence of an external force, but that external force is periodic in this case. So the external force is also periodic external force. That is the difference. Okay, so forced vibrations, the vibrations of a body which take place under the influence of an external periodic force acting on the body. So in this definition, mentioning this external periodic force is very important. You simply say external force, it will go wrong, because in natural vibration also it is the same thing. Okay, now examples. What are the examples? When a stem of a vibrating tuning fork is pressed against the top of a table and tuning fork produces a forced vibration in the tabletop. The tabletop has much larger vibrating area than the tuning fork. So the forced vibrations of the tabletop, that they are those forced vibrations. Now the tuning fork is vibrating periodically, and this tuning fork produces forced vibrations in the table. Okay. Now, the vibrations produced in the diaphragm of a microphone sound box with frequencies corresponding to the speed of the speaker are forced vibrations. When the speaker is speaking, the diaphragm of the microphone also starts vibrating. That is called forced vibration. In a guitar, when an artist plays on its strings by his fingers, the vibrations in them cause forced vibrations in the air enclosed in the hollow box. So they are forced vibrations. In the stringed instruments provided with a hollow sound box containing air, strings are made to vibrate by plucking and which are periodic in motion, and these strings, these vibrations, periodic vibrations of the string produce forced vibrations in the air in the box, sound box. So, the difference between natural and forced vibrations, the vibrations of a body in the absence of any resistive or external force are called natural vibrations. Forced vibrations of a body in the presence of an external periodic force are called forced vibrations. Okay. Then the natural frequency of the frequency of natural vibrations is remains same, constant, whereas the frequency of vibration is equal to the frequency of the applied force. The amplitude of vibration remains constant in natural vibration. The amplitude of vibration depends upon the frequency of the applied force. Okay, so now next we will be running on a very important concept called resonance, which is a special case of forced vibrations. Resonance. When resonance is a special case of forced vibrations, when the frequency of the external applied periodic force on the body is equal to its natural frequency of the body, then the body readily begins to vibrate with an increased amplitude. See, here resonance is a special case of forced vibration. That means a periodic force, a periodic vibration in a body produces these forced vibrations, no doubt. But what is the difference? It is the resonance is a special case of forced vibration. Now, what is the special case? When the frequency of the applied periodic force on the body is equal to the natural frequency of the body. Then the body starts vibrating with the increased amplitude. This phenomenon is known as resonance. The vibrations of large amplitude are called the resonant vibrations. When does this happen? When the frequency of the external applied periodic force is equal to the natural frequency of the body. Then resonance occurs. Okay. So, resonance is a special case of forced vibration. It is a forced vibration only. Okay. But what is the difference between force and this resonance vibration? Force vibration, the natural frequency of the body need not be equal to or is not equal to the frequency of the external periodic force. Whereas in resonance, the natural frequency of the body is equal to the frequency of the applied force. Okay? Now, condition for resonance. Resonance occurs only when the applied force causes forced vibration in the body and the frequency of the applied force is exactly equal to the natural frequency of the vibrating wave. That is the condition. The frequency of the applied force must be equal to the natural frequency of the vibrating body. Okay. Now children, today I will stop here. In my next part 3, I will teach about the applications of resonance. Hello children, Vanashi ma'am is back with your physics class, sound part 3. In part 1 and part 2, I have already explained to you about the how sound travels, what are the different properties of sound waves, light waves. Then I have already discussed about reflection of sound waves. I have discussed the important topic echo with you, uses of echo by bats, dolphins, and different fishermen, etc. Sonar has been discussed with you. These are all very important topics and concepts very often asked. Then I have taught you about vibrations, natural vibrations, damped vibrations, forced vibrations, and I have also taught you about resonance, a very important concept. Now I will give you some examples of resonance in this part, which are also very important. Some examples of resonance. Let me just brush up once again. What is resonance? Resonance is a special case of forced vibrations. When the frequency of the externally applied periodic force on the body is equal to the natural frequency of the body, then the body starts vibrating with a increased amplitude. This phenomenon is known as resonance. Okay, so the vibrations of the large amplitude are called resonant vibrations. So this is what is the phenomenon of resonance. So when does the resonance occur? When the applied force has the same frequency as the frequency of the body on which the force is applied. So as I told you, for example, suppose a ruler is stamped to the edge of the table, and if the ruler is made to vibrate, and if the frequency of the ruler's vibration matches with the vibration of the table, then natural frequency of the table, then the table also will start vibrating and producing sound waves of, so that is more amplitude or bigger amplitude. So that is called resonance. Now let us take some examples. So basically, for resonance, the frequency of the applied force on the body must be equal to the natural frequency of the body. Then the body will start vibrating with a larger amplitude, and that is called resonance, and that vibrations are called resonance vibrations. Okay, now let us take some examples. It will be more clear. The first example is resonant vibrations of pendulum. Okay, now what is this? Now if two pendulums of same length, suppose, are suspended from a rubber string, and one pendulum is made to vibrate, the other pendulum also starts vibrating with a larger amplitude and in same phase because of resonance. Means what? Suppose two pendulums of same length, so naturally, since they are of same length, their amplitude will be natural frequency will be same. Okay, the natural frequency of vibration will be same. Now if this one of the pendulum, now if it is struck, and since they are attached to the same rubber string, so what will happen? The other one also will start vibrating, and it will start vibrating with a larger amplitude, because they both have the applied force has same amplitude as the same frequency as the other one. So that is why it will start vibrating with bigger amplitude, or it is called resonance. So for example, suppose this is the rubber string, resonant vibrations of pendulums. Okay. Now suppose this is the rubber string, and suppose two pendulums of same length are attached to the rubber string. Suppose this is A, we call this as B. Okay. Same length are suspended from this rubber string. This is the rubber string. And now suppose this pendulum A is made to vibrate. Okay. Then the other pendulum B also starts vibrating, but then B starts vibrating with a larger amplitude because of resonance. Okay. Next, second example is resonance in machine parts. Now, for example, take a vehicle. When a vehicle is driven, the piston of the engine makes to and fro motion at a frequency depending upon the speed of the vehicle. Now, the vibrations caused by the movement of piston are communicated to all parts of the vehicle. There are so many parts in the vehicle. It is just possible that at certain speed of the vehicle, some parts of the vehicle may have natural frequency of vibration equal to the frequency of the to and fro movement of the piston. So the piston is making to and fro movement. It has a frequency, and sometimes the frequency matches with the natural frequency of some parts of the vehicle. At this particular speed of the vehicle, that particular part of the frame starts vibrating vigorously due to resonance, because its frequency matches with the frequency of the piston, which is moving up and down. Okay, and then you hear a rattling sound is heard. Sometimes when the car is moving with at a high speed, sometimes you hear some rattling sound. If this part is not tightly fixed, such vibrations may cause the part to drop out, or my part may get damaged. To stop these vibrations, the speed of the vehicle is changed so that the condition of the resonance is disturbed. Okay, so thus resonance can occur in any kind of machine while operating in particular conditions. So we have to be very careful. Is that clear, children? Okay, now the third example. Now the third example is resonance in a stressed string and sound box of musical instruments and sonometer. So resonance in a stressed string and sound box. This is present in which musical instruments? Like guitar, sitar. Okay, these are all stringed instruments with sound box. Okay, of now, a vibrating string by itself produces weak sound which cannot be heard at a distance. Therefore, all these musical stringed instruments such as guitar and then your sitar, etc., which such as guitar, sonometer, are all provided with a sound box, that is a hollow chamber. Okay, the box is so constructed that the column of air inside it has a natural frequency which is same as that of the string stretched on it. So this hollow box in sitar or something like this. So the air, the volume is so adjusted that the air inside this has the air column has the same natural frequency as that of the string that is stretched here. Okay. Okay. So now when the string is made to vibrate, the air column inside the box is also set into forced vibrations, the frequency of which is same as that of the string. Since the sound box has a large area, it sets a large volume of air into vibrations. Okay, are you getting my point? So now because of resonance, the amplitude of the amplitude of the vibrations of the air column is much larger and a large sound is produced because of resonance. Okay. Now this was the third example. Then the fourth, resonance in air column and tuning fork. Resonance in air column and tuning fork. Now suppose when the frequency, suppose there is an air column, like for example, water is filled up. So this is the air column. Okay. Now if a tuning fork is brought here, okay, and vibrating tuning fork. So what happens if now the air column, the length of the air column is fixed in such a way that the natural frequency of the tuning fork and the air column matches. Okay. So what happens when you bring a tuning fork near the mouth of that tube containing that air column, so because of resonance, a loud sound is heard. Why? Because the natural frequency of the tuning fork matches with the natural frequency of the air column. That is why the air column vibrates with larger amplitude because of resonance, and so a large sound is heard. Then the next example, resonance in a bridge. This is very often asked, very important. When a troop crosses a suspension bridge, you have seen suspension bridges, the bridges which are suspended by means of huge iron wires or iron ropes, you can say. So such suspension bridge, when a troop of soldiers, when a group of soldiers cross such a bridge, the soldiers are asked to break their steps. Why? Because the reason is that when soldiers march in steps, each soldier exerts a periodic force in same phase, and therefore the bridge is put into forced vibrations of because and when the frequency of the marching soldiers and the natural frequency of the bridge become equal because of resonance, because resonance happens and bridge will start vibrating with a large amplitude due to the resonance, and the suspension bridge may collapse. So that is why the soldiers are asked to break their steps, so that there is a difference in the natural frequency of the vibrations caused by the movement of the marching soldiers and the natural frequency of the suspension bridge, so that they do not never become equal to each other and resonance does not occur. Otherwise, if resonance occurs, the bridge may collapse because the bridge will start vibrating with larger amplitude. When the natural frequency of the suspension bridge and the marching soldiers becomes equal, then the resonance, due to resonance, the suspension bridge will start vibrating with larger amplitude. So as a result, it may collapse. So that is why the soldiers are asked, whenever they are marching through a suspension bridge, they are asked to break their steps so that the natural frequency gets disturbed. The natural frequency does not get equated to the natural frequency of the suspension bridge. Then the sixth example, resonance in, then the sixth example, resonance in radio and TV. The tuning of a radio and TV receivers is based on resonance. The radio and TV receivers have electronic circuits which produce electromagnetic vibrations, the frequency of which can be changed by changing the values of the electronic components. Okay. When we want to tune a radio or TV receiver, we merely adjust the values of the electronic components to produce vibrations of frequency equal to that of the radio waves which we want to receive. Okay. So, because when we receive the radio waves, then we can hear. Okay. When both the frequencies match, resonance occurs and only the energy of the signal of that particular frequency is received from the waves present in the space, leaving the signals of other frequencies which do not match with the frequency of the receiver circuit. The signal received is then amplified in the receiver set. Now, it leads to resonance with the natural frequency of vibrations of the, because of the resonance, we can then hear clearly. Okay. Is that clear? So, these are the examples of resonance. So, basically resonance occurs when the natural frequency of the applied force or the applied vibrating force and the white body, when the natural frequency matches, only then the resonance occurs and the body starts vibrating with larger amplitude. Usually, very often asked question is, when a troop crosses a suspension bridge, the soldiers are asked to break their steps. Why? So, you have to explain why they are asked to break, so that the natural frequency of the marching troops and the natural frequency of the bridge, suspension bridge, should not become equal. Otherwise, the suspension bridge may collapse. Then another often asked question is, why are stringed instruments like guitar or sitar provided with a hollow sound box? So that again, otherwise only the stressed string cannot produce large sound. That is why the air column is in the sound box is adjusted in such a way that its natural frequency is equal to the frequency of the vibrating stressed string. So, when the string is made to vibrate, the natural frequency of the air column also matches with the frequency of the vibrations of the string, and therefore resonance occurs and the air column vibrates with larger amplitude, and so a larger sound is heard. Okay. So, these are the most often asked questions from this resonance topic. Then we will learn more concepts like characteristics of sound. Okay. The next topic, characteristics of sound. Now, there are three characteristics. Okay. One is loudness, second pitch, or in our common language we call it shrillness, and the third is quality. The scientific term is timbre. Okay. So, these are the three important characteristics of sound. So, let us learn about each one. Now, loudness. Okay. Loudness is the characteristic by virtue of which a loud sound can be distinguished from a faint one, both having the same pitch and quality. Okay. So, with the help of loudness, we can distinguish two different types of sounds with different loudness. That is, loudness is a characteristic by virtue of which a loud sound, you can always make out which is a loud sound, which is a faint sound, isn't it? So that is the property of sound, that is called loudness. So loudness is the characteristic of sound which enables us to distinguish what? Which distinguish between a loud sound and a faint one. Okay. Now suppose, for example, take a tuning fork, strike it softly. You will hear a feeble or soft sound. Bring it in front of a microphone. Okay. Now, so what will you see? Now strike the same tuning fork hard, where in front of the microphone. A loud sound is heard. Okay. So then you are able to distinguish. So this is the property or the characteristic of sound which enables you to differentiate between loud and faint sound. Okay. So if you again graph them, if you again draw the graph of two waves having same frequency and same waveform but having different amplitude, so the loud sound corresponds to the wavelength, larger amplitude of sorry, not wavelength, larger amplitude. So loud sound always corresponds to larger amplitude. So if suppose you are given like this, so here time you have, here you have amplitude. This is the amplitude. So this is suppose one sound wave and another sound wave okay, suppose this is A, this is B. So if you are the amplitude of this is this, isn't it? So now if you are asked to identify which sound wave will have loud sound, or you can hear the sound loudly, is B, isn't it? Why? Because B has larger amplitude than A. So therefore this will be soft or faint sound, whereas this will be loud. Okay. So larger the amplitude, the loudness will be more. Okay. So loudness of sound depends upon the amplitude of the wave. Loudness of sound depends on the amplitude of the sound wave. So usually this is a very important statement for fill in the blanks. So for amplitude they will give you the blank and they will give you the option amplitude, frequency or time period, amplitude, something they will give, but amplitude is the correct word. Loudness depends upon the amplitude of the wave. Okay. Then we will learn another important term called intensity of sound. Now, the intensity of a sound wave at a point of the medium is the amount of sound energy passing per second normally through an unit area at that point. Okay. So, basically the intensity is what? The intensity of sound wave at particular point in a medium, say in air or in water, in whatever is the medium, is the amount of sound energy passing per second normally through an unit area at that point. So, suppose in this medium at this point the intensity of sound will be the, suppose the amount of sound that is passing normally, normally per unit area through that point per second. So, that is called intensity of sound. Okay. So, greater the energy carried by the sound wave, greater will be the intensity of the sound. So, intensity of sound wave, how do you define? It is the amount of sound energy. Sound is a form of energy. So, the amount of sound energy passing per second normally, that is perpendicularly, through an unit area at that point. At this point, if you want to measure the intensity, it is the amount of sound energy that passes through this point through unit area per second. Okay. So, this units are the intensity of sound. How do you measure? By the amount of sound energy that is passing through through the unit area, okay, through 1 centimeter square or through 1 meter square area at that point. So, the amount of sound energy that passes through unit area per second at that point is called the intensity of sound. Okay. Now, next topic is very important that we are going to learn. The next topic is subjective nature of loudness and objective nature of intensity. The loudness of a sound depends on the intensity, that is the energy conveyed by the sound wave near the eardrum of the listener. Now, and the sensitivity of the ears of the listener, that is also important. Okay, sensitivity of the listener, sensitivity of the eardrum of the listener. Thus, loudness of sound of a given intensity may differ from listener to listener, isn't it? Those who hear hard or those who have hearing problem, for them a loud sound also may be heard as a faint sound, which to us is a loud sound. So, it differs from person to person. That is, sound of the same intensity may appear to be of different loudness to different persons. Further, two sounds of same intensity but of different frequencies may differ in loudness even to the same listener, because the sensitivity of ears of a person is different for different frequencies. Okay. For normal ears, the sensitivity is maximum at the frequency of 1 kilohertz. So, when is our sensitivity maximum? At when the frequency is 1 kilohertz. So, this is again an important statement for fill in the blanks. For normal ears means who do not have any hearing problem. For normal ears, the sensitivity is maximum at the frequency of 1 kilohertz. Okay. Thus, for a sound wave, loudness has a subjective nature, that is, it depends on the listener. while intensity, being a measurable quantity, has a objective nature. That is why the loudness differs from person to person. So it is subjective. Okay. Whereas intensity, which can be measured. So whichever it can be measured is called objective nature. Okay. But the same loudness, you may call it very loud, somebody may call it faint who has listening problem. So that is subjective in nature. So that is why the for a sound wave, loudness is of subjective nature, while the intensity is of objective nature. This is again a statement important for fill in the blanks. The loudness of sound wave is of subjective nature, while the intensity of sound wave so while the intensity of sound wave is measurable, that is why it is of sound objective nature. So the intensity of sound wave is of objective nature. So what happens, in fill in the blanks, they give, suppose the loudness of sound wave is of dash nature, and in brackets they will give both subjective objective as option. Similarly here, while the intensity of sound wave is of dash nature, and they will give again options as subjective and objective. So you have to choose the correct word in the correct blank. So loudness is of subjective nature, while intensity, which is measurable, is of objective nature. Okay. Now we'll learn about factors affecting the loudness of sound. The next topic is factors affecting the loudness of sound. Now the loudness of sound heard at a place depends on the following 5 factors. Loudness is proportional to the square of the amplitude. Loudness is proportional to the square of the amplitude. Loudness varies inversely as the square of the distance from the source. So loudness varies inversely as the square of the distance from the source, and loudness depends upon the surface area of the vibrating body. So a large vibrating area sends forth greater amount of energy, hence larger the surface area of the vibrating body, louder is the sound heard. So in again, loudness is again directly proportional to the area of the vibrating body. Okay. So and loudness also depends on the density of the medium, and it depends upon the presence of resonant bodies. Okay. So loudness also depends upon density also. So loudness is again directly proportional to the density. So loudness is directly proportional to the density also. This is area of the vibrating body. Loudness also is directly proportional to the density of the medium through which the sound wave is passing. Okay, and loudness also depends on the presence of resonant bodies. Why? Because the presence of resonant bodies increases the loudness of the sound. Okay, so these are the factors which affect the loudness of sound. Now we will learn noise pollution. You must have heard this word a lot number of times. Noise pollution. Now, disturbance produced in the environment due to undesirable loud and harsh sound of level above 120 decibel from various sources such as loudspeakers, siren, moving vehicles, etc. is called noise pollution. So, a constant hearing of sound of level above 120 decibel can cause headache and permanent damage to the ears of the listener. So, the safe limit of level of sound for hearing is from 0 to 80 decibel. Sound of level 30 decibel to 10 decibel has a soothing sensation, while the sound of level 0 decibel represents the lower limit of the hearing. So, the limit of hearing should not be confused with the limit of audibility. The limit of audibility refers to the frequency range of sound from 20 Hz to 20 kilohertz. This I taught you in the very beginning of the lesson. That is the limit of audibility. Okay, that is from 20 Hz to 20 kilohertz is the limit of audibility of sound which a man can hear. While the limit of hearing is the lowest level of loudness, that is 0 decibel, which a man can hear. Okay, and soothing or comfortable is sound of level up to 30 decibel. Okay, and if you hear a constant sound of levels above 120 decibel, then that is called noise pollution. It can cause headache and permanent damage to the ears also. Okay, then the next important term is pitch or shrillness. Pitch is that characteristic of sound by which an acute or shrill note can be distinguished from a grave or flat note of same loudness. So, pitch is that characteristics of sound by which an acute or shrill note can be distinguished from a flat note of same loudness. Sometimes we say, no, somebody, the singer's voice is very shrill, she sings with a shrill voice or she shouts with a shrill voice. Whereas she sings, sometimes we come and she sings with a flat note. So, that is the meaning of pitch or shrillness. Pitch is considered only in reference to the musical sounds. As I told you, this is most often used with reference to musical sound. Each musical note has a definite pitch. If the pitch is high, the sound is shrill, and if the pitch is low, the sound is flat. Okay? If the pitch is high, the sound is shrill. Okay, and if the pitch is low, the sound is flat. Okay. So, pitch of a note depends upon the frequency. Two notes sounded on the same instrument with some same amplitude will differ in pitch when their vibrations are of different frequencies. Now, for example, in string instruments such as piano, violin, guitar, the frequency of vibrations of string depends upon the tension and thickness of the string. They can produce notes of different pitch by changing the thickness and tension of the strings. Okay, so a note of higher pitch can be obtained by vibrating the string no higher pitch. Okay, so with us using the same instrument, a note of higher pitch can be obtained by vibrating the string under high tension or by vibrating a thinner string. So sometimes, very often, you must have observed the musicians changing the tension in the string, that is, they keep tightening the screws so that the tension in the strings is increased. Then in case of a flute, a lower note is obtained by closing some more holes so that the length of the vibrating air column increases. As the water level in a pitcher kept under a water tap rises, the length of the air column decreases. So the frequency of sound produced increases. That is, sound becomes shriller and shriller. Thus, by hearing the sound from a distance, one can get the idea of water level in the pitcher. Then the voice of a woman is usually of higher pitch than that of a man. So these are the examples of pitch. Now, pitch also has subjective nature and frequency has objective nature, because again frequency is measurable. So, pitch is not same as frequency. The pitch depends on the sensation as perceived by the listener. So, pitch depends upon the, again, sensation of the listener. It may be different for a sound of a particular frequency or to different listeners. That is, pitch is of subjective nature. On the other hand, frequency is a measurable quantity. Therefore, it is a objective in nature. So, pitch is subjective in nature and frequency is objective in nature. Okay. Then the third one, quality or timbre. Quality or timbre. Quality or timbre of a sound is that characteristic, is that property of sound which distinguishes the two sounds of same loudness and same pitch but emitted by two different instruments because of change in their waveforms. Okay. So, what is the quality or timbre of a sound? Two sounds, they may be having same loudness, same pitch, but they are emitted by two different instruments. So you can immediately make out that this sound is from this instrument and this sound is from this instrument. You can make out which sound is from a flute and which sound is from a guitar. So that is called the quality, that characteristic by which you can differentiate the type of instruments from which the sound is emitting. That is called quality or timbre. So, the quality of a sound wave or musical sound depends on the waveform. Okay, so different musical instruments have different waveforms. Now, next is music and noise. Now, music is a pleasant, continuous, uniform sound produced by the regular and periodic vibrations. Okay, music is a pleasant, continuous, and uniform sound. It's a pleasant sound, continuous sound, and uniform sound produced by regular and periodic vibrations. Okay, for example, the sound produced by a violin, piano, or flute. These are all musical notes, musical sound. Noise, the sound other than musical sound is called noise. It is a sound produced by irregular succession of disturbances. It is usually a discontinuous sound. It is discordant and unpleasant to the ears. So, that is the difference between music and noise. So, music is regular, smooth, pleasant to the ears, whereas noise is harsh, discordant, and unpleasant to the ear. Music is produced by vibrations which are periodic, whereas noise is produced by vibrations which are irregular. All the component waves and in music, all the component waves are similar without any sudden change in their wavelength or amplitude. And this in noise, the component waves change their characteristics, that is their wavelength and amplitude. Okay. So, the examples of music, as I told you, sound produced by all musical instruments. An example of noise, the sound produced by aeroplane, road roller, industrial machines, etc. Okay. So, thank you children for watching. In my next class, I will be doing the numericals based on this chapter. So, go through the topics, and in our next class or in the part 4, I will be doing the numericals. Thank you children. Take care. God bless you.